Imagine, for a second, sitting around a late-night campfire, just looking up at that vast, incredible canopy of stars. For generations now, we've shared this beautiful, really comfortable story about where all of that came from. The Big Bang. I mean, it's basically the single most successful description of reality we've ever come up with. But that's actually not what we're doing today. In this explainer, we aren't here to just celebrate it. We're here because, right now, that beautiful, comfortable story is starting to fracture. So welcome. Let's take a journey into the Big Bang's beautiful cracks.
Okay, let's dive right into this with a number, 67. Or, to be super precise, about 67.4 kilometers per second per megaparsec. Now, don't even worry about those units right now. The only thing you need to know is that this is the universe's current expansion rate. And we get this number by looking at the oldest possible light from the very infant universe and then calculating forward across time. It is a stunningly precise prediction.
But here's the massive paradox. When we look at the late universe, like the universe right now, and we directly measure how fast nearby galaxies are actually moving away from us, we get a completely different number, 73. Now, think about this. These are two measurements of the exact same expansion rate, made by two different teams using literally the finest instruments our species has ever built. They are supposed to be the exact same number. But here's the part that should honestly stop you in your tracks. As our telescopes have gotten sharper and our measurements have gotten more precise, these two numbers did not move closer together, they actually drifted further apart.
And to put all of this into perspective, think about this tiny 5% slice of reality. It really grounds this whole mystery in a deeply human way. Because that 5%, it contains everything you have ever seen. Every star and every photograph, every planet, every cloud of gas, every single atom in the chair you're sitting in right now, and the body of literally every person you have ever loved. All of it, just 5% of the cosmos. The other 95% is made of two totally invisible things, dark energy and dark matter. And the craziest part? Nobody on Earth actually knows what either of them truly is.
So, here is our roadmap for this explainer. We're going to cover the paradox of precision, a cathedral with cracks, the missing 95%, how the universe disagrees, and finally, a thrilling first draft.
Let's get into Section 1, the paradox of precision. The closer we look.
As we just laid out, the Big Bang is the most successful theory in the history of science. I mean, it predicted the temperature of the infant universe to better than 1 part in 1,000. That's incredible. Yet paradoxically, the closer we look at it today, the less comfortable it becomes. The better our eyes, the stranger the picture. And this is a really crucial framing for us. The theory isn't failing because it's a bad theory. Usually, when a theory is right, zooming in makes all the little discrepancies vanish. But here, looking closer with our incredible modern telescopes is actually manufacturing the disagreements. Our instruments are finally sharp enough to see the edges of our own understanding.
Moving on to Section 2, a cathedral with cracks, the model's foundation.
So cosmologists built this mathematical model called the lambda CDM model. You can think of it like this stunning, monumental cathedral built on just 6 numbers that flawlessly predict the universe. But the deepest crack in this whole cathedral sits right at the very beginning. If you rewind the universe, obviously it gets smaller, denser, and hotter. But right at the very first frame, the math just breaks. It gives us what we call a singularity. 0 size, infinite density, infinite temperature. But here's the secret. Infinity in physics is almost never a real measurement of the actual world. It's an error message. It's basically the mathematical sound our theory makes when it hits infinity and breaks. So the map of the universe literally has a tear right where the story is supposed to begin, signaling the limits of our math, not reality itself.
And it doesn't stop there. Moving just past the beginning, we hit these foundational anomalies that the model really struggles with. First, the horizon problem. Basically, patches of the early sky that have never been in contact somehow share the exact same temperature to a staggering precision. Then, the flatness problem. The early universe was balanced on a geometric knife edge so incredibly fine it completely defies explanation. Next up, the antimatter imbalance. Energy makes equal parts matter and antimatter, right? So they should have annihilated each other completely, and yet somehow a tiny, unexplained surplus of matter survived. Enough to create us. And finally, the lithium problem. The theory predicts 3 times more lithium than we actually find in ancient stars. These are massive, glaring mysteries that are either quietly patched over by cosmic inflation or just left totally unanswered.
Which brings us to Section 3, the missing 95%, the invisible universe.
Remember that invisible 95% we talked about earlier, the dark sector? It is profoundly bizarre that the overwhelming majority of reality is just completely invisible to us. You've got dark matter making up about 27%, acting as this invisible scaffolding holding galaxies together, and then dark energy making up 68%, actively pushing the universe apart. And honestly, this brilliant quote perfectly illustrates the situation with dark energy. In our models, it's often represented by the Greek letter lambda. But as the source material points out, it's really just a placeholder wearing a Greek letter. It's a confession dressed up as physics. Basically, to make our beautiful equations match the night sky, we had to assume that the largest ingredient in the entire universe is something we completely don't understand, driving space apart while remaining totally mysterious.
All right, section 4. The universe disagrees. The Hubble tension.
Now we arrive at the single most stubborn crack that keeps cosmologists awake at night. The crucial point here is this deep contradiction. We have the early universe prediction sitting at 67 and the late universe direct measurement sitting at 73. The universe is giving us one growth rate from its infancy and a totally different, completely irreconcilable rate for its current state. And the gap between them has actually reached 5 sigma. In physics, that is the absolute gold standard for a real undeniable discovery. It's not a fluke. It means the bridge we walk across to get from the infant universe to today, the standard model itself, might literally be missing a plank.
And guess what? The newest telescopes are finding even more missing planks. Let's walk through it. Step 1. Evolving dark energy. The massive DC survey recently hinted that dark energy might not actually be a constant at all, but rather it's weakening over time, which totally breaks the core assumption of our model. Step 2. Impossible early galaxies. The brand new James Webb Space Telescope is finding galaxies that are too big, too bright, and forming way too soon, completely breaking our expected timeline of structure formation. And Step 3. Anomalies in the ancient light. The cosmic microwave background itself has these strange, inexplicable smudges and cold spots that, according to the math, just shouldn't be there.
And the deep, unresolved fractures just keep piling up. When quantum physics tries to predict the vacuum energy of empty space, it is off by 120 orders of magnitude. That is a 1 followed by 120 zeros. It is literally the most spectacular failure of quantitative prediction in human history. Meanwhile, the oldest, most impartial light of the universe, the cosmic microwave background, has features that appear curiously, almost impossibly aligned with the plane of our very own solar system. It turns out the foundation of this incredible mathematical cathedral was never perfectly smooth to begin with.
But perhaps the most profound crack of all connects directly back to you. There's this idea that the arrow of time is a debt we owe to a mystery. The only reason time flows forward for us, the reason you can remember yesterday but not tomorrow, is because the universe began in an extraordinarily ordered, low-entropy state. The odds of this happening by pure chance are so mathematically vast, they literally break language. When you sit there and feel time passing, you are experiencing the direct, personal consequence of an initial condition that physics simply cannot explain.
Let's wrap things up with Section 5. A thrilling first draft. A privileged place? I want to be really clear here. All of these beautiful cracks do not mean the Big Bang is a lie or that it has somehow been debunked. The core reality of a hot, dense, expanding universe is absolute bedrock. But as we look at the whole timeline, from the very moment of the Big Bang to the release of the first light at 380,000 years, to those impossible early galaxies at 300 million years, all the way to our present day at 13.8 billion years, we have to realize that our current mathematical model is just an incredibly accurate first draft. We're finding anomalies at almost every scale. But here is the magnificent takeaway from all of this. To live right now, in this gap between a phenomenally successful old theory, straining under new data, and a totally new theory that hasn't quite been born yet, that is a deeply romantic and privileged place to be. We are standing exactly where physicists stood right before Einstein changed everything. So, I want to leave you with this final provocative thought. Right now, we have more clues, more anomalies, and sharper instruments than ever before in human history. The universe isn't making less sense. It is patiently handing us the puzzle pieces for a much deeper kind of sense. The next Einstein might be alive right now. They might even be watching this very explainer, ready to write the rules we haven't even read yet. So I have to ask, what will the next draft of the universe look like?